All right, today we're diving into one of the most fundamental forces in the entire universe. Yeah, we're talking about that invisible architecture that literally powers our modern world, the electric field. So, let's get right into it.
You know, it all starts with those little zaps and weird attractions you see or feel every day. I'm talking about that tiny spark you get from a doorknob, or how a balloon just magically clings to your hair, right? Well, that's not magic, it's physics. Pure physics in action. And today, we're going to break down exactly how it all works. Okay, so to understand any of these forces, we've got to start at the very beginning. We need to look at the fundamental building block of literally everything electric, and that is electric charge. So, what exactly is charge? Well, the easiest way to think about it is as a basic, fundamental property of matter, kind of like mass. You've got protons, which carry a positive charge, and you've got electrons, which carry a negative charge. Simple as that. Everything, and I mean everything we're about to discuss, starts with these two key players.
Now, charge isn't just a free-for-all. It plays by a very specific set of rules. First up, it's quantized. That's a fancy way of saying it comes in these tiny indivisible packets. You just can't have half a charge. It doesn't work that way. Second, it's conserved, which means you can't create or destroy charge. You can only move it around. And finally, its value is invariant. It doesn't change no matter how fast it's zipping through space.
Okay, so we've got these positive and negative charges. The big question is, what happens when they actually get near each other? How do they, interact? Well, let's take a look at the rulebook.
And that rulebook has a name. It's called Coulomb's law. This cool little equation tells us the exact strength of the force between any two charges. And it really just depends on two things: how strong the charges are, and, this is the big one, the distance between them. The key thing to remember here is that the force gets way weaker the further apart the charges get, and it drops off really, really fast.
So that's the strength of the force, but what about the direction? That's what we're seeing here. If you have two charges that are the same, two positives or two negatives, they push each other away, they repel. But if you have one positive and one negative, they pull towards each other, they attract.
So it all boils down to this one simple, super elegant rule that governs pretty much everything, from the atoms in your body to the electronics in your phone. Opposites attract, likes repel. That's it. That's the fundamental dance of electric charges.
But wait a second. This whole thing leads to a much deeper question. We know charges attract and repel each other, sure, but how? How does one charge know that another one is even there, especially when they're separated by totally empty space?
I mean, really think about it. There's nothing physically touching them, right? So what's carrying this force from one to the other? The answer? Well, it's one of the most powerful and profound ideas in all of physics, the field.
So instead of imagining charges acting on each other directly, from a distance, physicists came up with this idea. A charge actually modifies the space around it. It creates what we call an electric field. You can think of it like an invisible region of influence. Then, any other charge that happens to wander into this field feels a force. The field is basically the middleman that communicates the force across empty space.
Okay, but if it's invisible, how do we visualize it? Well, we draw these things called electric field lines, and there's a simple convention. The lines always point away from positive charges and towards negative charges. So the direction of the line at any given point tells you exactly which way a tiny positive charge would get pushed if you dropped it right there.
Right, so drawing the field for just one or two charges, that's simple enough. But what happens when you have a whole mess of charges, like billions and billions of them on a metal sphere or a giant flat sheet? Suddenly, the math gets really, really messy.
Trying to add up the effects of every single one of those billions of charges would be pretty much impossible. But thankfully, physicists came up with an incredibly elegant and powerful shortcut that just slices right through all that complexity.
And that amazing tool is called Gauss's law. What it says, in a nutshell, is this. If you draw an imaginary bubble around some charges, the total number of electric field lines poking out of that bubble tells you exactly how much charge is trapped inside. It's just a genius way to relate the field to the charges that are creating it.
And this is where it gets really powerful. For situations with nice, clean symmetry, like a perfectly charged sphere, Gauss's law makes the problem almost trivial. It lets us sidestep all the hairy calculations and find a clean, simple answer for the electric field.
It's a beautiful, beautiful shortcut that saves us from a mountain of difficult math.
Okay, so whenever you have a force, that also means there's energy involved, right? Pushing charges around against an electric field takes work, it takes energy. And this brings us to a really cool idea, the concept of an energy landscape.
Think about it this way. A charge sitting in an electric field has potential energy. It's just like a bowling ball being held at the top of a big hill, has gravitational potential energy. And the amount of energy that charge has depends entirely on where it's located within that field. And this graph is a perfect way to picture what's going on. Imagine a positive charge creates a kind of energy hill around it. Now, if you want to bring another positive charge closer, you have to physically push it up that hill. You're doing work, and you're storing energy in the system. The potential, which we call V, is basically just the height on that hill at any given distance r.
And that, my friends, brings us to a word you have definitely heard before, voltage. Electric potential, or voltage, is just the potential energy per chunk of charge. It's a property of the space itself. It tells you how much energy a charge would have if you placed it at that spot. It's a map of the energy landscape.
So here's the big connection, the crucial takeaway. The field and the potential are two sides of the same coin. This equation right here basically tells us that the electric field, which is what causes the force, is really just a measure of the steepness of that energy hill. So where the hill is steepest, that's where the electric field is the strongest. And just like a ball, charges naturally want to roll downhill to a place with lower energy.
And all of this leaves us with a pretty mind-bending final thought. We started this whole journey with a simple static shock from a doorknob, and we've ended up here, with the idea that what we call empty space isn't empty at all. It's actually buzzing with these invisible fields, a complex energy landscape that's dictating the motion of every charged particle in the universe. It really makes you wonder, doesn't it? Is space ever truly empty?